a pretty good time to get started. So let's just begin by reviewing what we did last time. So we spent the beginning of class answering some questions about homework 3. And if you all have any more questions about that, please ask them. So typically, and one of the things that happened last time in class was at the end of class, like at least 4 or 5 people came up to me to ask me more questions about the homework assignment. But if one of you has a question about something, probably half the class has a question about the same thing. So if you have a question about a homework assignment or how to do something, just ask it in class. And that way, a lot of people are going to benefit from your answer as opposed to, just a couple of people after class. So that was homework 3. Then we talked about homework 4, which is your next homework assignment. So it's online now. You can go and download it. And it's about large-scale machine learning. So in that homework assignment, what we're going to do is we're going to take a database of 50,000 handwritten digits and try to automatically classify from the image, like which digit it is. And we spent the majority of class talking about things like how the k-means classifier works, how the multinomial logistic classifier works, and how you can get those to work along with your code that you wrote for stochastic gradient descent. So the plan is for you guys to use the exact same code that you wrote, and you might have to edit it a little bit to make it work better, but essentially the same code that you wrote for homework 3 for stochastic gradient descent, and then use it on the machine learning problems in homework 4. So one of the main differences between the two homework assignments is that in homework 4, there's a lot less description of how to organize your code. And in general, that's what's going to happen from now on. So far I've been doing a lot of cut-pasting of the object descriptions and the function descriptions, and all of that's going to go away with homework 5 and after. So it's just going to be do this, and it's going to be up to you guys to organize your code in a nice way so that you can reuse it potentially for other problems. And then just at the end, we had just a few minutes to talk about parallel computing in Python. And we're essentially going to do most of that again later today. But what we're going to start with today is going over homework 3. But before I get into that, are there any questions about anything?
In one of the videos, you told that you have discussed about returning a function to a function.
Yeah. So we're going to see an example of that today when I go over my code. So a function is an object in Python the same way that anything else is. And so you can pass it around the same way that you can an integer or an array or anything else. And you certainly did a lot of that like for this last homework assignment, right? Because the Sgd code has to take in, so for example, a projection function and a step function that returns like the various step sizes, right? So we're just passing around those functions like objects.
Can you call the initialization method in other functions?
So the initialization method gets called once when the object is created. And that's it. If you want to call some part of it, what you do is you make another method and you have the initialization method call that. And then if you want to do it again, you just call that other method, if that makes sense. Okay, other questions? Okay, if not, let's, so one more thing before we go through homework 3, which is I've posted online on Canvas a practice exam. So we're going to have our first exam in about a week. So it's scheduled for October 4th. And it's going to be an open internet exam. So you don't have to be here. You can be anywhere that you want to take this exam. You can use whatever tools that you want to take the exam. And the way it's going to work is it's going to come online on Canvas at a particular time, at our class start time. And it's going to be due 2 hours later. And if you have to turn it in within those 2 hours, or it's basically going to disappear from Canvas. So you won't be able to turn in your assignment. So based on my past experience of teaching this class, people usually benefit from some amount of practice taking these kinds of exams because they haven't done it before, right? So most of the exams you guys have probably done have been pencil and paper kinds of things. And so that's why the practice exam is there. Please take a look at it. And we'll do a solution of it in class sometime next week, okay? maybe even on Tuesday next week. So my recommendation is to try to do the practice exam over the weekend. Okay? Okay, so then let's take a look at some of the solutions for homework 3. Okay, so this is what my parabola code looks like. And I pretty much cut-paste the various function descriptions and object descriptions into your homework assignment. And so one thing I have to tell you about sort of organizing code is typically when I'm writing this, I kind of start with just a blank file, right? And so I write some stuff, and then as I'm writing, I think, oh wait, there's like a way better way to organize this. And then I might move a bunch of code around, like reorganize the way that the objects work. And so expect to do that on future homework assignments when you're writing your code, right? So there might be a much nicer way of organizing things than the way that you started. So in the initialization function here, we just take in the center and the coefficients. So the coefficients get saved, the center gets saved. So zeros like is a function I use quite often. So it returns an all zero array that's the same shape as the array that you passed in. So it's very useful for doing things like that.
So basically if you pass a 2 cross 3 range,
yeah,
2 cross 3 matrix,
that's right.
Zeros.
That's right. That's right. Okay, so then AskEval just evaluates the function. So let's see the interesting things here. So this was a question that came up briefly in class last time, which is when you write vectorized code, somebody instead of passing in a single point, like this, so that's how you should pass in a single point to vectorized code, right? They might pass it in just like that, right? Just as a single array that has the point. And so what my code here does is just check if the dimension is 1, and if it is 1, then it sort of changes it to the right vectorized format. Okay, so all of you hopefully did this without any for loops, right? So it's just a dot product and then a square, right? Okay, so stochastic eval, like we're going to use this in the next assignment. Right here, you can just return AskEval. Okay, so for grad, similar thing in terms of vectorization at the beginning. And then the gradient is the coefficients times 2 times x minus the center. And then a number of you asked questions about this, which is, so is the gradient of a parabola, is it bounded? No, it's not, right? So we talked about this briefly in class last time. So the gradient, or a parabola kind of looks like this. And sort of the higher that I get here, the bigger the x gets, the steeper the parabola gets, right? And if you didn't bound the gradient, your code probably diverged for some of the examples that you ran, right? And so that's what's going on here. Is I got the gradient as a vector, and then I wrote a function that basically bounds it. So what this does is it looks at the magnitude of the gradient and decreases it to some constant. So we'll take a look at this function in just a moment. Yeah, Pratik.
If you bound the gradient that we get is no longer an expectation, it remains the gradient.
That's right, but it turns out that the algorithm still works. Yes.
Shouldn't this bound grad thing be in the Sgd code?
It is in the Sgd code.
But, like when you're using it, you should be bounding the gradient. Here we are just calculating the gradient, so we should be rewriting the gradient.
That's also like a great point. So what you're saying is that you did it in the do step function, right? So you called grad, and then you bound it there, and that also makes perfect sense. Maybe even better way to organize it than this. Okay. So let's take a look at stochastic gradient. So this is the first one that picks a uniformly random coordinate and then returns the gradient in that coordinate. So let's read over these lines. So in the first one, I'm picking, let's imagine doing this for vectorized code, right? So I have a whole bunch of x zeros. I have to pick a different coordinate for each of the x zeros. So I'm not sure, but perhaps many of you did the following. So let me just erase this. Give me a second. So perhaps many of you did this. So let's say this is 0, 1, 2. This is 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we have a bunch of points that got passed in. You may have picked a single coordinate for all of these points. So how many of you did that? Okay, great, right? Because these should be totally separate runs of stochastic gradient descent, which means we have to pick a separate one for each one of the points that got passed in. And so that's what this code does. So it's picking an integer between 0 and the shape of the coefficients, and it's picking as many of them as there are rows in X. Okay, so I'm picking one coordinate for each one of the X's. And then here I'm just going to find sort of the index that we're going to use in take in a little bit. So this sort of matches up which x goes with which one of these random points, right? So the 0th row of the x vector goes with the first one. The first row of the x vector goes with the second one, and so forth. Okay? So here answer is 0 is like x because it's going to be a gradient, so it should have the exact same shape as the x function, the x that got passed in. And then let's see what happens here. So here I'm using a bunch of SciPy indexing tricks. And I'd be curious to kind of know how you guys did it, because maybe you used very different sort of SciPy techniques to write this without a for loop, okay? But what did I do? I said, take a look at these rows of answer and these columns. And that makes sense, right? Because answer is all zeros, and it's going to be all zeros except for those rows and those columns. Okay? And there, it should be the C's times SciPy.take of C times 2x minus SciPy.take of the center of the C indices, right? So what am I doing here? I'm taking the right coefficients and the right x's and multiplying them together to put into the right parts of answer. So this was why I introduced you guys to SciPy.take a couple of lectures ago, because it helps me, or at least it helped me avoid a lot of for loops in writing these Sgrad type codes. So any other ideas? I'm just curious about how you wrote this. So did anybody, who used a for loop? Who didn't use a for loop? Okay, for those of you that didn't use a for loop, did you do it exactly this way or did you do it some other way? Okay. Well, in that case, hopefully it's useful. Okay, so and then we bound the gradient the same way that we do with the other one. So so let's take a look at our next function, which is a superclass of our original parabola class, right? So what happens here? We have our we get our x, and then we need to project each of the x's on a uniformly random direction. So over here, we compute the gradient for all of the x's. And then here, we pick the uniformly random direction. So we do our normal trick where we pick a bunch of standard normals, and then I change them into unit vectors. And I just wrote a little function to change them into unit vectors. And so then we have to do the actual projection, and that's what's happening here, okay? And so that's just the direction times the dot product of the gradient and the direction, okay? And then we return the bounded gradient. Does that make sense? Say again?
The unit break thing is
Yeah, it's my own function. Okay, so just the only maybe interesting thing here is just overriding, right? So the only difference between the two parabolas is how we're going to compute the stochastic gradient. And so there's no reason for me to rewrite any of the code other than just that one function, right? And so that's what it does. And so if somebody told me to go and write the stochastic gradient like this, like grad f plus nu, where nu is some normal, that's n-dimensional normal, what would I do, or what would you do? Yeah, you would say like parabola with normal noise or something like that, and you would right here go parabola with normal noise, and you would just it would be subclassed from parabola, and it would have a different Sgrad. Okay. Okay, and for actually creating the various movies and the frames for the movies, I put it all under the parabola in the parabola file. So if name equals main, and then these are all the various for loops. But before we go through these, let's go and take a look at the Sgd code to see how that works. Okay, so maybe a couple of interesting things here is that, so how did you guys store the history of your x's? So to create the plots in the movies, you have to have a history of all the x points that the gradient went through. Right, so how did you do it? Okay, and that's what I did originally as well. But in the next assignment, we're going to be running gradient descent on a 800 dimensional example, potentially on many points for something like 30,000 iterations or 3,000 iterations. And so what happens is that history gets bigger and bigger and bigger and eats up memory in your laptop, right? So because I was, at the same time as implementing your parabola code, I was working on that more complicated next homework assignment, I did the collections, or instead of using a list, I used some other tools in collections. So collections has a object in it called a queue. So if you're familiar with a queue, what you can do with a queue is put objects on one end and remove objects from the other. So that way I can have a constant history size without sort of changing things. Now, you may have implemented a constant history size as well because that was one of the parameters that was passed into the function. But how did you do that?
What I did was I checked if like if we know the history size ahead of time. So if his size is -1, then I created a list. Otherwise, I created an array. Okay.
And so what happens if as I'm doing steps, I sort of go larger than the history size? So let's say the history size is 50, but I do like 700 steps.
I'll start deleting things, like overwriting things.
So how do you delete them? So that's kind of the main question, is because the way that you do that could make a massive impact on your code. Okay. And then how do you take off the first element of the list, right? Because you're adding lists at the end using append. And to remove the first element of the list, what's going to happen every once in a while is that your entire list is going to have to get copied. And that's the main difference between queue and collections and removing the first element of the list. Yeah?
Can we just use, there's a command called delete del.
It's the same reason. The reason is that every once in a while when you do that for a list, the entire list has to get copied. Because the way that lists work in Python is the following. So let's say this is my list in memory. And what happens is the computer allocates some piece of memory, and maybe your list is only using sort of this part, okay? And then when you append something, it's going to take a little bit more of the memory on the right. And when you delete something, it's going to leave a little space here on the left, right? So every time that you append something, it's going to go here, and every time that you delete something, it's going to take something away from here. So this thing sort of starts shifting over to the right, and eventually when it hits the end of the what was allocated in terms of memory, the whole thing has to get copied. So that's an expensive operation because you have to iterate through the whole list, copying all of the integers in it. So one thing that's a little bit more efficient is to use the queues and collections, which is what I did. And we're going to see some other interesting things associated with that. Okay, so one of you asked me about returning functions from other functions, right? So this is what this function is doing. So step size, right? So step size takes in two things. The gamma that's going to be on the denominator of the step size, and then the start, which is how big my initial step is going to be. And inside of here, it creates another function, which is the step function, and that takes in which step I'm in. And here, it returns the initial step size times 1 over n to the gamma. And here, I'm returning sfunc. So that's how I create a function that returns another function as a result. Does that make sense? Okay, so unit vec, you all should be pretty familiar with. We've done this in class several times. You get in a list of vectors, you compute their norms, you normalize them, and then you return the answer. And the only thing that's going on here is sometimes the norm is 0 because I often start my code at x equals 0, and I don't want to get a bug. And so this just kind of checks if you're starting at x equals 0. And if it is, then the normalization is 0. Okay, so bounding the gradient. So here we get, again, our list of vectors, and the constant that basically says how big of a gradient is too big. So by default in my code, I set it to 1, but this could be any constant, right? It could be 10, it could be 30, whatever I choose, and the algorithm's going to work just fine with that constant. So we compute the norm. The answer starts out as all the vectors that got passed in, and if the norm is bigger than whatever constant was given, then this is the normalization to the constant length that we said, right? So this code here normalizes it to unit length, and then I multiply it times that length to get it to whatever, size 10 or whatever it is. And then again, here I'm just checking if any of the vectors were all 0, and then I return the answer. Okay, so then let's look at Sgd. So one potentially interesting thing is we have sort of two different ways of passing in a function into some class, right? And both of those are present here. So one is afunc. So what kind of object is afunc? So for our current project, it's a parabola. But it's really any object that has things like .sgrad on it, .feval, .sfeval, and so forth, right? And I don't care if it's a parabola or something else, as long as it has .sgrad. And what kind of object is sfunc? That's an actual function, right? So, and in fact, both of these in some sense are functions, but this is an object that I'm looking for .sgrad, and this is something that I'm going to call directly, right? But both of them really are kind of like passing a function into stochastic gradient descent. Okay, so let's take a look at what's going on here. So I save the function that's going to give me the sgrad. I set the start to a particular set of points that were passed in, set the step function, set the projection, and if a projection wasn't passed in, I create an identity projection. Okay, so that's like if nobody passed in, the projection is just whatever whatever point you're in, and then save the his size, whether we have a small history, the number of data points to use for sgrad, whether to keep objective history, and then I reset the whole history of the object. Okay, so let's read what some of these do. So set start just sets the x0 value. And my reset, all it does is, yeah.
What's the point of calling reset in the initialization method?
Oh, because I might want to use the same Sgd object, but reset it, kind of restart from the beginning, which is maybe a question that one of you guys asked a little earlier, right? So how do I recall a part of my init method? So this was a useful part of init that I might call from the outside. So here, I set up all of these queue objects that I mentioned earlier, right, where you can put stuff on the left and take stuff from the right. Whether, if I am going to keep the objective, I keep my objective history, it also gets a queue object. And then we get self.keepObjective, which is that one. Okay. So then let's take a look at doStep. So what does it do? It takes a look at the most recent point that we were on. It calls Sgrad. It computes the step size. It takes the next step. It does the projection and increases n by 1 so that next time that I'm called, I'm going to decrease the step size. And so after doing all of these steps, all we have to do is update the history, right? So this is checking if small history was true or false. And if it's true, then we're going to append all of these things. And if it's false, we're just going to keep the X history. This is just some code for keeping the history of the objective function values. And then this is all the code for making sure that my history doesn't get too big. So this might be somewhat interesting. So we check if the history size is bigger than 0. And if it's not self.smallHist, then we're going to pop stuff from the left, which keeps it within some maximum size. So the main deal is that while you guys sort of did del or something like that to remove the thing that was on the leftmost end of the list, here I'm using this pop left. Okay, so n steps just calls doStep n times. So hopefully everybody did this. It's kind of part of code organization, right? If you've written some piece of code that does something, like just generally never cut, paste it. So get average solution. So this is something that might be interesting to you, which is that in Python, slices are objects. Okay, so what I mean by that is, let's say A is some array, and then we do that array 2 to 4. This right there is a slice object. Okay, and you can create them by doing things like this: slice 2 to 4. And so I could do A of slice 2 to 4, and it should return the same thing. And so what this code is doing here is just doing those slices, but for that queue object. So this is the queue object. I'm iterating over it, and the slice that's getting taken is from the length of the history minus how many ever things I need to average up until the end, okay? And those are all the things that need to get averaged to return a solution. So one of you asked me, why do we average things when we return a solution from stochastic gradient descent? So can somebody answer that question?
Maybe because since you are calculating stochastic gradient, those points, like the directions may be randomly in different directions, so all those points may not be nearby. So we are just taking the, averaging it out and...
That's great. That's a great explanation, and that's exactly right. So here is an example. So let's say that this is the center point that is going to be our optimal point, right? So maybe one part of Sgd or one step of Sgd is there, and the next one 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 is there, right? They're kind of bouncing around the optimal point. And so if we take the average of them, it turns out that you can prove in general that it has a lot less variance around the optimal, okay? So it turns out that sort of the more averaging you do, the less variance you're going to get. And that's why we have that function in Sgd. And maybe some of you played with averaging 1 or not, or more than 10. But one interesting thing for you to try, if you're curious, is you could plot the objective function values of the parabolas as your code's running. And it's going to kind of be decreasing, but it's going to be bouncing around quite a lot. And then the next thing you could do is try to plot the same objective function values, but not of the x's, but of these averaged solutions. And you'll see that they're like much, much nicer, like much smoother. Okay, so then getSolution does the following. So one problem with this algorithm, and if for those of you that have taken optimization classes like convex optimization or nonlinear programming, a key question with an optimization algorithm is when do you stop, right? And I never told you in class when to stop, right? Like we showed that it converged, but is like 50 steps enough? Is like 100 steps enough? How many steps is enough? And so that's what this function does. It's going to compare two consecutive solutions, and if the objective function value didn't change very much, then we're going to say we're done. Except it doesn't make sense to compare single consecutive solutions of Sgd, because each of those has quite a bit of randomness, right? So what this function does is, if you think of this as the history of all the points that the algorithm has gone through, and this is the most recent, it might compare sort of the average of these to the average of those, okay? So I'm going to compare the objective function value here to the objective function value there. So can you tell me why these two boxes aren't right next to each other? Why wouldn't I sort of, like if I'm trying to do, like trying to compare whether the objective function value changed very much, why wouldn't I sort of take the last 10 and then the ones that were between 20 and 10?
So nearby points, the correlation will be more.
Exactly. There's a lot of correlation between those points because stochastic gradient was over here for a while, right? And then it might sort of bounce to some other place. And so that's why there needs to be this part in the middle. Sometimes people call that burn-in or like mixing time that just says like how far from my previous point do I need to be before I sort of sample my next point, okay? And so that's what all of these various parameters are saying. So it's saying how large of a window should you average and how many windows should there be between the latest window and the previous one that you're going to compare. Does that make sense? And I hope that everybody understood that from reading the project. Question?
I didn't understand. So W interval is basically the difference between those two boxes?
That's right, but in units that are equal to the window, right? So this means that I'm going to average the last 10, I'm going to skip 10 of the history, and average the ones that are between 30 and 20.
Basically 1 times 10.
That's right, exactly. And then the absolute tolerance and relative tolerance basically say how close should those two function values be for me to say that I'm pretty much done, right? So let's read how this works. So my history size has to be at least this big, so that's what's going on here. And if I haven't taken that many steps, I need to do that, so that's what's going on here. And while we're not done, we're going to do this checking. So this is checking one of the windows, this is checking the other window, and this is evaluating the function at those two windows, okay? And then we need to check whether they're within the absolute and relative tolerances of each other. So what is the absolute tolerance? Well, I have to subtract those function values, look at the absolute value of that, and make sure that it's less than absolute tolerance, okay? So why am I using scipy.all here? Yeah, so what does scipy.all do? Yeah, it tests whether all array elements along a given axis are evaluated to true. So why am I doing scipy.all here? It's because the x's are vectorized, right? So my x history actually has a x history for like all the x points that I've been doing. And this function is only going to stop when all of them are within the absolute tolerance and relative tolerance. Does that make sense? So this is computing the differences for all the x values, and here we're checking if all of them are within the absolute tolerance. So similarly with the relative tolerance, so here we're just taking a look at the fraction, and then we're just making sure that it's within that percentage of each other, okay?
So now are you comparing the objective function or just the two points?
Just the objective function. So I'm not looking at the distance between the points. I'm only looking at the objective function value. And I'm making sure that the objective function value has kind of stabilized. There hasn't been too much decrease from the last window to the current window.
So then, I mean, the FO and FU should be one number.
Say again?
I mean, FO and FU, because they are just the objective function for the average 10 points.
Yep.
So they should be a number.
They are, but there's one of those for each x.
Oh. Yeah.
Right, because I might have like 4 x's or something like that. Okay. So, if we're not done because these absolute and relative tolerance are unsatisfied, then we're going to do some more steps, okay? And then it's going to return whatever the most recent solution is. Okay, and this was just my plot function to create each of the frames of the movie. Maybe the most interesting thing here is like this alpha value. So how did you guys make the lines kind of fade out? Like, did you use alpha values? Because Pratik told me he used colors instead. So he kind of had a linear gradient between the black lines and the white lines, and then did that. So did everybody use alpha values? Yeah? Say, oh, you haven't gotten to that part. How many have completed the homework assignment? How many have not completed the homework assignment? Okay, this is great. This should be super useful for you guys, right? So the homework assignment is due tomorrow, and I hope that looking at this is very helpful. Okay.
When is it due tomorrow?
Tomorrow evening. Tomorrow evening. Yeah. Well, I think it's midnight or something like that. But okay, so that's pretty much the only interesting thing in plot. And so let's take a look at, yeah.
You used the Q structure and there was this pop left. The Q structure, any other pop doesn't make sense, right?
No, you could do pop right, because in Qs you can remove
you
things.
enter through this side, but you come out.
That's right.
Side, right? So, okay, pop right means entering.
No, pop right means you can remove. So this particular...
Leave out of the...
Yeah, so this particular Q data structure in Python, you can do it either way. So you can like put stuff on the left or right, and it's just as efficient whichever way you want to do it. Okay, so let's take a look at my code to actually create the various frames for the movies. So here I'm creating the parabola object. Here I'm creating the Sgd object that passes in the parabola, passes in the start point and the step size. And then I had 200 frames in my movie, and each frame, like the optimizer, is going to take one step. So it's just clearing the matplotlib function, and then plotting the optimal location, and then calling optimizer.plot. So then the next few look exactly the same, really. Like, really the only thing that's changing between any of these for loops is what the parabola object is, sometimes what the number of steps is, and definitely what the name of the file that I'm going to save that particular frame, okay? So this was the first part of the movie, the second part, the third part, and the fourth part. So this one, for plotting the 3D parts, you might have to do some reading of documentation, which is a really important part of this class, right? Because one of my main goals is not so much to kind of teach you all of the things that are available, but more to have you practice reading on your own and learning these things on your own. Yeah, that's the last one that does several points in parallel. Okay, so any questions about any part of the homework assignment? And I know you all haven't completed it, and so let me ask another question. So how many of you talk to another person in class while doing the homework assignments? That's extremely useful, okay? Like strongly, strongly encouraged, because they're reasonably difficult assignments, and so you'll learn a lot, I think, from talking to each other to solve these things. Okay, other questions before I go on to parallel computing?
So are we going to see this video online?
Which one?
This video, today's video.
Oh yeah, I'm definitely going to post this. Why?
Oh, okay. I need to review anyway.
Yeah. So the other thing is, one of you, or maybe several of you, came up in class and asked me to slow down a little bit, okay? The only way I can do that is if you ask me questions. And like I said, if you have a question, probably a lot of other people in class have that question. But unless you guys ask me the question, like I'm just going to sort of keep going with the next material that we have, right? And so, to continue from there, unless there's any questions, we're going to talk about parallelizing code in Python, which is going to be your next homework assignment, which is out today, but it's due in several weeks from now. So it's going to be due after the exam, okay?
So you said the video would be what about the code? Because there's a lot of
Absolutely not. Okay, for a number of reasons. One, I want you to do it.
Well, I know you want, when we're done with the assignment.
So it's also no, because in the next assignment, I want you to use your Sgd code, which is part of the point of having you build up a code base.
Right.
But after those two assignments, yes, I'll post it on Canvas if you'd like to see it. Yeah.
Free to change our code after this discussion, right? Like,
Oh yeah, yeah, you can change it however you want. Absolutely.
I'm just mildly concerned because if you wrote inefficient code to begin with and are somewhat behind the eight ball, then you're even more behind the eight ball as you go along.
So that's where talking to other folks in class, I think, would help a tremendous amount, right? I guarantee you there's at least one of you in here that's going to write potentially like more efficient code than what I did, right? And so the only way that that's going to the only way that you'll get better at these things is basically by doing it, right? And me explaining it is going to be totally different than somebody else explaining it. Okay, other questions? So if not, let's continue talking about parallelization in Python. So just to review a little from last time, we're going to use the ipython.parallel module to run computations on potentially multiple machines and have those machines communicate with each other. So that's going to be part of your next homework assignment, okay? So the basic setup of IPython parallel is the following. First, you start a cluster, and a cluster looks a little bit like this. We have a number of engines, 0, 1, 2, 3, and a controller. So the only thing that the controller does is it helps communication between the client and the engines. So the client can send a request to the controller, for example, execute this code on engine 0, and then the controller sends that code to engine 0, which executes it, and then potentially an answer gets returned back to the client. But after the client submits this request, the client doesn't have to wait for an answer. It could continue executing some other code, and then sometime much later sort of check if that answer has completed, and then use the answer, okay? So let's go through some examples of how to actually set this up. And I'm definitely going to post this code online because it might help you with your next homework assignment. Okay, so the first thing that you have to do is start the Ipython parallel cluster. So the way we're going to do that is with IP cluster start n equals 4. So let me do that. Okay, and you get a bunch of debug messages that basically tell you you're starting this cluster, it has a controller, and it has 4 engines. If I wanted 5 engines, I'd have 5 engines and so forth. Now, these engines don't have to be on the same machine. You could start engines on a different machine, and the only thing that you have to tell the engine is where the controller is, okay? And then the engine and the controller are going to talk with each other to make sure that they introduce themselves to each other, and then they could work from there. Okay, so the next thing that we have to do is we have to start the client program. So the way to start the client is to import Ipython parallel. And then create a client object. Okay, so now we have this client, and it's already connected to the controller. Okay, so the first thing that there are 2 different ways of interacting with the client. Okay, so we've created this client object. There are 2 different ways. So one way is for the client to explicitly tell the controller, execute this code on engine 2. Okay. And then the controller is going to send that code to engine 2 to get executed. Another way that the client interacts with the controller is execute this code, and I don't care which engine it is. And then the controller makes a bunch of decisions to make sure that these engines are what's called load balanced, so that each of them is kind of running code at about the same rate. Okay? Okay, so let's create a direct view, which is basically you have to explicitly tell which engine you're going to execute code on. Okay, so one useful thing is you could do the client object.ids, and that returns to you the name of how many engines there are. So here I know there are 4 engines, because that's how I started the IP cluster. Okay. So here's an example of sending some code over to the engines to get executed. So you can think of each engine as a little Ipython interpreter, kind of the exact same way that I started an interpreter on the command line, right? So all of them right now, they just started and they haven't imported anything, they haven't done anything. And right here, we're going to send them a command, and when you say dv.execute, it says send it to all of them, okay? So I'm going to tell all engines to import SciPy. But let's take a look at the code here a little bit. Perhaps one of the interesting things here is the block argument. Okay, so the block argument basically says, should the client wait for an answer from the engines, or should it keep going? Okay, so let's do this both ways. So let's do dv.execute import SciPy, and let's do block equals true. And let's see what the answer looks like. And the answer is an object called an asynchronous result. And it says that this asynchronous result has finished. So all the engines have finished doing that import. But if I do block equals false, and I look at answer, okay, so here it finished because those engines were really fast at executing that command. But potentially it might not have finished yet. Okay, so that's importing SciPy. But now let's actually execute some more interesting things on these engines. So I've created a variable called length, and it's right here on the client program. Okay. And what I want to do is I want to push that variable to all the engines, right? I want to have each engine have a variable in it that's called length, and that it has the same value as whatever the client has. So that's what push does. So let's execute this code. And as you can see, this is just a push result, so it may take it some time to get executed. Sorry, question?
Why not just use the execute again?
Why don't we use execute again? Oh, you can, but the main difference is that with execute, I have to pass in all the code as a string. Here, I'm not passing things as a string. So imagine that length is some gigantic SciPy array with, 100,000 coordinates. Then push is going to push all of that out without me having to change it to a string. Does that make sense? So one of the main limitations of parallel computing is you have to think about how much information is getting sent between the between the controller and the engines, right? So if there's too large of objects that are getting communicated, then that's going to be really slow because the network is going to be slow. So the main idea is to kind of send small pieces of information, but have a large amount of computing happen at each of the engines. Okay, so then let's execute some more things here. So what are we doing? We're again executing some code on each of the clients. We're doing a range, and we're storing that in answer in each one of the engines. Okay, so here's a great example, right? So we called execute, but it didn't return finished yet. And that's because all the engines aren't done yet. And so you can take a look at this async result object, and it has a function on it called get, which basically is going to force you to then wait for all the engines to complete. So I'll show you that in maybe just a minute. So maybe let's do it like this. So answer 2 is equal to that. And let's say that this is the result object. And the reason get returns nothing is because that line returned nothing, right? It's not like it had a return value. Okay, so now I have answer on each of the engines, and I want to pull this value onto the client, right? So I want to go to all the engines and collect all the answer arrays back into the client. So again, this is going to be asynchronous. So here the result's finished, and if I print r.get, I get all the arrays from all the 4 engines. Does that make sense? And you can do that with blocking mode as well. And if you don't want to keep calling block, you could say block equals true. Okay, so one important example, or let's first take a look at the load balanced view, and then I'll show you a useful example that you might use in your next homework assignment. So remember that in the direct view, you can specify which engine it is. So one way that you can do that is you could do client 0. Let's say D2 is client 0. So now I'm going to only talk to engine 0, okay? And let's say that D2 dot push answer equals 5. And I oftentimes just have to remember how these things work by looking them up. So here I've pushed answer equals 5 onto engine 0. And now if I do my pull, then on engine 0, answer is 5. But on all the other engines, answer is that array. Does that make sense? So that's how you can specify a particular engine to execute this on. Okay, so let's take a look at the load balanced view. So again, it works very similar to the direct view. you have to go to the client object and create a load balanced view. So there it is. And what we're going to do next is we're going to sort of store some data on each of the in each of the engines, but in a different way than the push that we saw earlier. So let's create a module called Datastore. Okay, and so here we've had, we created our load balance view, and here we're saying execute this only on engines that can import Datastore and import SciPy. And we're going to define this power function that's going to take the power of Datastore.a to the x. Okay, so let's make a be 2. Okay, so we created the power function. And then we're going to use map on the on this load balance view controller. So how many of you are familiar with the map function and what that does? So what map does is it takes this function and calls it on each one of the arguments. Okay, and for a load balanced view, like there's how many computations to get done here? There's 3, right? I have to call power on 1, I have to call power on 2, and I have to call power on 3. And what load balanced view is doing is taking these computations and splitting them up as evenly as possible between all of the engines. So if I had 300,000 computations here, like about a fourth of them should get executed on each engine. And if you imagine the engines running on different machines, like maybe one's a slightly older machine, it runs a little slower, and one's a slightly newer machine, it runs a little faster, then the newer machine is going to get more of the computations than the older machine, okay?
Does the controller sort of take some feedback, like there is a feedback loop?
Does the controller...
Like as in, while they are executing those operations, so they might return some results, and then based on, when they return, they will say, okay, you can take more. So like,
oh, yeah, absolutely. That's exactly what it does, right? So if something gets completed, the load balanced view is going to send it more work. And so this was an asynchronous result, and then let's run that in parallel, and then let's print r.get. And here we get the answers of 2, 4, and 8, right? So it took a to the first, a to the second, and a to the third in different engines. Okay. So one interesting thing is on the client, you could take a look at the results object, and this is sort of a history of all the communication that the client or that the controller had with the engines. Okay, so these are all the various calls that we made to the various engines and the results that got returned back. So one of the things that's going to happen in your next homework assignment is when you do 3,000 steps of stochastic gradient descent and you're communicating with a bunch of these engines, this results history is going to get longer and longer and longer and longer until potentially you run out of memory. And I definitely ran out of memory when I was running it. So one useful thing is to just do c.results.clear. And that's just going to forget all the history of the communications. And so every once in a while, after you've collected all of the things that you've sent out to the engines, it's useful to clear the results so that your program doesn't run out of memory. And so this is a slightly different way of doing the same power function. So what does it do? It defines a function here that's power. Inside of it, it imports SciPy and Datastore and does power of Datastore.a to the x. And it's the same load balanced view mapping that we had before. Okay. Okay. So a really important concept is this concept of the Datastore module. Okay. The reason that that's useful is you can have the clients sort of maintain different memories in them. So in particular, one thing that you're going to have to do in your homework assignment is each one of the engines is going to have about 1/4 of the database of examples. So we have 50,000 examples of handwritten digits. 1/4 of that should go on engine 0, 1/4 of that should go on engine 1, 1/4 of that on engine 2, and 1/4 of that on engine 3. Okay? But how are you going to do that? So one way that you might think of is to do a push. And what's the problem with that? So here's one potential way of doing it. I have my client, it reads in the database, and it pushes 1/4 of the database to engine 0, 1/4 to engine 1, and so forth. So why is that kind of not a particularly nice way of doing it? Say again? So let's say that they don't fail. So let's say that they're not going to fail. So what's wrong with reading in the 50,000 examples in the client and then pushing it to one engine and then the next and then the next? Say again? So that's one thing, absolutely. Is like you might run out of memory on the client. What's another problem with it? There's another sort of huge problem with it. Yeah, that's a huge problem. It's an enormous amount of communication that's not actually necessary. So what usually happens when people write distributed code like this is instead of doing that communication, like on each of the engines on its hard disk, you sort of already put a piece of the data, right? And then what you do is you send a command over to the engine that says load your data, right? And then every engine is going to load sort of a different piece of the data because each of them has a different piece, like on their hard drive, okay? And that gets rid of the communication problem because the only communication that's happening is load your data. And the actual data is already stored on the engine, okay? So, and that's what you can do with a module like Datastore, right? So Datastore, for example, could have in it a function that's called load your data, right? And then when you call load your data on engine 0, it's going to do something, and load your data on engine 1, it might do something else. Load your data on engine 2, it might do something else, and so forth. And so that's one way that you might sort of create different data on different engines. So here's maybe an interesting example of doing that. So let's try to do this with a direct view. So what I'm going to do is define a function, let's say, and it's going to take in some arguments as input. And here it's going to import Datastore. And let's say that it's going to say Datastore my array, or my array is equal to SciPy dot arange, and let's say args 0. And then Datastore dot numEngines is going to be equal to args 1. So one thing I might do is create an array like this. So let's call it args for engines. So on engine 0, I might want an array of size 10, and the number of engines is going to be 4. On engine 1, I might create an array of size 20. The number of engines is 4. On the next one, it's going to be an array of size 30. The number of engines is 4. Then the last one's an array of size 40, and the number of engines is 4. And then I can do dv.map. Load data and args for engines. Okay, so what should I be expecting to happen after I execute this? So help me think through what I just wrote. Okay. So at the end of this, what kind of data should be on engine 0? That's right, and that should get stored in datastore.myArray, right? And it's also in datastore.numEngines is going to have 4, right? And similarly, it's going to be 1 through 30 for the third engine, and so forth, right? 1 through 40 for the fourth engine, etc. Okay, so let's try to run this. And if I call r.get, it's a bunch of nones because this function didn't return anything, right? I could have had this function return something, but it didn't return anything. So now let's take a look if those arrays got created correctly. So I'm going to do dv.execute import Datastore with block equals true. So I'm forcing all the engines to import Datastore into the main namespace. And then I'm going to just do, let's say, dv.pull datastore.myArray. Let's say block is true. Okay? So those are all the different arrays that I created on all the engines. Like the first one got 0 through 9, the second one got 0 through 19, and so forth. Okay? So this should be tremendously useful for your homework assignment. Because what you can do is, especially if you're running on a single computer, is you can have just one copy of the database in a directory. You start the engines, and then you do something like this where you tell each engine what fraction of the database to read in, okay? And then that's the way that you can have each engine sort of have a piece of the database that then you can run Sgrad on, okay? So one other thing that's going to help you with debugging is when I ran import Datastore, it executed correctly on all of the engines, but it might not. So the only reason that it executed correctly on all of the engines is because I started IT cluster in the directory where datastore.py is stored, okay? So if I had started this cluster on some other directory and I ran import, you can think of the engine sort of having their Ipython interpreter. It's running import, so it's going to look through that Ipython path or through the Python path to see if the module is there. And if it's not there, then it can't import it. So you're going to get an error. So the only reason this worked is because I had the whole cluster started in a directory where they could actually see that module and import it. Okay, so one last thing that I think might be quite useful for your next homework assignment is the following. Okay, so we're going to have something like, you're going to want to call Sgrad with 300 samples. So out of the 50,000 images, I want to sample 300 images to compute Sgrad. But I have these 4 engines, right? So here's engine 0, 1, 2, and 3. And I need to send in a uniformly random way. Like I need to split this 300 so that a part of it goes to 0, a part of it goes to 1, and a part of it goes to 2, and a part of it goes to 3. And so one way that you might do it is sort of do 300 over 4, something like that, and try to send that amount to each engine, okay? But we're going to do something slightly different, which is I want to figure out 4 numbers, like A1 plus A2 plus A3 plus A4, that's going to equal 300, okay? So I want 4 numbers that when I add together, I'm going to get 300. So how might I do that? And I want to do this in a uniformly random way. So, one way to do it is 111 and 297, but another way to do it is 211 and 298. And those have to be pretty much equally likely. So any idea how to do that? Okay, there are many ways to have 4 integers add up to 300. What I want to do is write a method or a function that's going to randomly figure out, uniformly randomly, 4 numbers that when I add them together, I'm going to get 300. And that's going to allow the client to kind of split the 300 samples across the engines. Okay? So any idea on how to do that? Yeah, exactly. That's exactly what we're going to do. So imagine that we have, here's our 300 count of samples. Okay, so what I'm going to do is exactly what you said, or something similar. Maybe we won't do it in exact detail, and you guys can sort of fill in the detail. But the detail is this. You sort of generate 3 or 4 uniformly random integers between 0 and 300. Okay? So let's say one of them is here, another one is here, another one is here, and another one is there. Okay? And let's say, because I want to split it up into 4, I'm going to just generate 3. Okay? So I'm going to generate 3 uniformly random numbers between 0 and 300. They're going to correspond to these arrows. Okay? So when I generated them, like the first one may have been this one, the next one may have, the first one may have been like 70, or let's say 200, the next one was like 100, and the next one was 70, right? But what I'm going to do is sort them so that the smallest is here, then the next biggest, then the next biggest, okay? And then to get my 4 numbers, A1, A2, A3, they're going to be equal to, sort of this distance is going to be A1, this distance is going to be A2, this distance is going to be A3, and this distance is going to be A4. Does that make sense? And so I suggest splitting your samples across the engines in this way. Okay? Okay, so that's it for today. Unless there's any other questions, thanks a lot for listening, and I'll see you all next time.